In this video, I'll be covering irreversible and reversible reactions, the concept of dynamic equilibrium, equilibrium shifts and separation techniques and methods in Chemistry 0620, Cambridge IGCSE, Topic 6, Rates, Reactions and Equilibrium. So let's begin by defining the difference between an irreversible and irreversible reaction. Irreversible reaction is the common reaction that we are familiar with when a product is formed and it is not easily converted back to a reactant. Straightforward, reactant to product, and hard to convert it back to the reactant. Reversible reaction is when the product is formed and it is easily converted back to the reactant. So reactant and easily converted back. So reactant to product and easily converted back to the reactant. We use two arrows to show both of the reactions, the forward reaction that forms the product and the backward reaction that decomposes to the reactant. For example, the Haber process. Nitrogen plus 3 hydrogen gives you 2 NH3 ammonia. Or the dehydration of hydrated cobalt chloride. Endothermic producing heat, absorbing heat, exothermic giving heat. Okay, so simply reversible reaction is a reaction that can easily be converted back to its initial state. Alright, so now let's understand the concept of dynamic equilibrium. Dynamic equilibrium is a state in the reversible reaction when three conditions are met. The concentration or amounts of the reactants and products are constant, not equal. The rate of the forward reaction is equal to the rate of the backward reaction. So remember what is equal and what is constant. Concentration and amounts of reactant and products are constant, but the rate of forward and backward reaction, or the speed at which it happens or takes place, is equal. Okay? So this only occurs in a closed system, so none of the participating chemicals are lost throughout the reaction vessel. As you can see, in an open system, particles or participating chemicals can be lost. In a closed system, there is no loss of the chemicals. Alright? I'll be skipping this example for now because it is not really necessary in understanding the equilibrium, as the concept is very clear. Again, to repeat, equilibrium is when the concentration or amount of reactant and product is equal, rate of forward reaction is equal to rate of backward reaction, occurring in a closed system, so none of the participating chemicals are able to leak out. Equilibrium shifts, we have two sides, of course, to the reactant, to the product side, right, to the reactant, left. The right shift is a forward reaction is favored. More product will form because it's going to the product side. So the concentration of the product will increase and more reactant will be used up. To the reactants or to the left side, backward reaction is favored. Less product will form, more reactant, concentration or amount of the reactant will increase. And yeah. Le Chatelier's principle. When a change in is made to conditions of a system at equilibrium, the system will automatically move to oppose the change. We use this principle in chemistry to predict the position of equilibrium when changes in temperature, pressure, and concentration are made to a reaction at equilibrium. This indicates the amounts of reactants and products at equilibrium depend on conditions of the reaction. And right now we will study the changes in temperature, pressure, and concentration, and how to identify what happens to the equilibrium position, where are the shifts during changes in temperature, pressure, and concentration. So again, factors affecting equilibrium change, the one we will study right now: concentration, temperature, and pressure. Does catalyst affect an equilibrium position? Well, that is a good point to understand. Catalyst will not affect the position of equilibrium, but it will speed up the rate of the forward and backward reaction. Like we said, the concentration and amounts are constant, but the rates of forward and backward reactions are equal. So catalyst will not affect the position of the equilibrium, it will not affect the amount or concentration of the product or reactant, but it will increase the rate of forward and backward reactions by the same amount. This will provide an alternative pathway requiring lower activation energy to initiate the reaction. Again, concentrations and amounts of reactants and products at equilibrium are not affected by the catalyst. This is a clear diagram that shows the effect of catalyst on equilibrium. So this is the forward rate reaction, and this is the backward rate reaction. Nothing is changed to the amount. The only difference is that there is lower activation energy, so the reaction will occur faster with a catalyst. Rate of forward and backward reactions are increased. This is a summary of the effect of equilibrium position using temperature, pressure, concentration, and catalyst, but I will go through them in depth right now. Concentration and equilibrium change. If you increase the concentration, equilibrium will shift away from its side. If you decrease the concentration, equilibrium will shift towards its side. What does this mean? Well, let's interpret the cases, case 1 and case 2. In case 1, we will increase the concentration of A plus B is a reversible reaction to D plus E. Let's try and increase the concentration of B. So equilibrium will shift away from its side. Increase the concentration of B, equilibrium will shift away from B towards the product side. So product is favored and amount of product, amount of D and E will increase. If concentration of D is increased, it will shift away from D, going to the reactant side. The reactant side is favored and amount of reactant A and B will increase. In case 2, when the concentration is decreasing, now A plus B using the same equation, reversible reaction to D plus D. If we decrease the concentration of D, it will shift towards its side, so the equilibrium will shift towards D, towards the product side, and more product will form. If the concentration of A is decreased, equilibrium will shift towards its side, towards the reactant side, and less product will form. Favored is the reactant, more concentration or amount of the reactant. Backward reaction is favored. Alright. Temperature and equilibrium change. So when you're looking at equilibrium change from a temperature perspective, the first thing I want you to do is determine whether this reaction is an exothermic or an endothermic reaction. So step 1, identify the delta or change in enthalpy. If the enthalpy change is exothermic, negative, then the heat is produced on the product side. If the enthalpy change is positive, heat is produced on the reactant side. Okay, temperature. This is the second step. Temperature. If the temperature is increased, equilibrium will shift away from the heat side. If the temperature is decreased, equilibrium will shift towards the heat side. So when you have a negative enthalpy change, if you increase the temperature, it will shift away from the heat towards the reactant. If you decrease the temperature, it will shift towards the product, and vice versa for the positive enthalpy change. Let's have a look at this example, example number 1 in this reaction. So this is the Haber process where we're forming ammonia. This is an exothermic reaction, hence heat is released in the product side. Determine the equilibrium change when the temperature is increased. According to the rule, temperature increase will result in the equilibrium shifting away from the heat side. Heat is on the product side. So again, firstly check if the enthalpy change is negative, so the reaction is exothermic. Use the above rules to answer. Equilibrium will shift towards the reactant, towards the left side, away from the heat side, because it's an exothermic reaction. Pressure and equilibrium change. So a change in pressure will only be affected if the number of gas moles in both reaction is not equal. So in the both reactant and product side, if the number of gaseous moles is not equal, it will be affected by change in pressure. Okay, now the ruling is somewhat the same. Okay, if you sorry about the camera, if you increase the pressure, it will shift to the less gas mole side. Decrease the pressure, it will shift to the more gas mole side. So in this Haber process, we have 4 moles in the reactant, 2 moles in the product. Increasing the pressure will shift it to the product side, less moles. Decreasing the pressure will shift it to the reactant, more moles. All right. Separation techniques. So we have finished with the equilibrium, dynamic equilibrium, and rates of reaction, reversible reaction parts. Now for the last part of topic 6, rates, reactions, and equilibrium, we'll be talking about separation techniques. So we will go through 5 separation techniques: filtration, crystallization, distillation, fractional distillation, and paper chromatography. Right, so beginning with filtration. Filtration is a method to separate and collect insoluble or undissolved solid from a heterogeneous mixture of the solid and liquid solution. So basically you are collecting insoluble solid that is not able to dissolve in a heterogeneous mixture from the solution. Example, sand from sand and water. The steps are simple. Place a filter paper in a filter tunnel above the beaker. Pour the mixture of insoluble solid and the liquid into this filter tunnel. The filter paper will allow small particles to pass through the tunnel. It will leave some small particles behind as the residue. Wash the residue by distilled water and dry the residue by the oven till all the water evaporates completely and when the mass stops decreasing. So I think filtration is quite clear here. Let's move to crystallization, a method to collect and separate soluble, dissolved, so solid that is able to dissolve from its solution. First, heat the solution to reduce the amount of solvent by evaporation and let the crystals form. Then cool it down to for more crystals to form, lowering the temperature and solubility, and then make filtration, these steps, to collect the residue of crystals, allowing the residue to be dried to be removed and any impurities. This is crystallization. I think that was also quite clear. Distillation is a method to separate the solvent, the liquid, from the soluble solid. So it's almost like a reverse of the previous ones. Okay, from a homogeneous solution or mixture. Example, water from seawater. So we use a condenser in this method. Solution is heated and the pure water will evaporate, producing water vapor that will rise through the neck of the round bottom flask. This vapor passes through the condenser where it cools and condenses, turning into pure water collected in the beaker. Once all the water is evaporated from the solution, only the solute is left behind. Fractional distillation. Fractional distillation is a method to separate two or more liquids that are miscible with one another. Basically, when the boiling points of the mixtures are close. So the solution is heated to the temperature of the substance with the lowest boiling point first. Then the substance with the lowest boiling point will evaporate first. Its vapors will pass through the condenser where they are cool and they become separated, leaving the components of the mixture behind. While collecting the desired substance, thermometer will stay constant at temperature of the lowest boiling point of the substance. Once all the desired substance evaporates, temperature will begin to rise again. Paper chromatography is a method to separate substances with different solubilities in a given solvent. So you have a solvent and there are many substances inside. You need to separate them based on their level of solubility, based on their rates of migration in a solvent on a filter paper sheet. So first you set up a chromatography paper as shown. This is the chromatography paper. You draw a line in pencil, not in graphite. This is a reference material and you add some ink. Then you lower the paper into a beaker with appropriate solvent and wait for the solvent to travel up the paper. After that you analyze the chromatography and just make your measurements of the RF value. So here are some facts. Substance with the highest solubility travels first. The origin line again must be with pencil because graphite is insoluble and it will affect your result. Origin line must be above the solvent level to avoid losing the sample by dissolving in the solvent. Here's chromatography again, separation depending on solubility. So you have the solute paper, you put inside the solvent, you have the drop of mixture, origin line must be in pencil, not graphite. And then you have the levels of solubility. A is the least soluble as it stays down, E is the most soluble as it rises up to the highest level. Solvent front is the maximum distance traveled by the solvent. You can use the RF value. So basically, from the solvent front up till this point is the this is the solvent front. Up till this point is the distance traveled by the component. This is the distance traveled by the solvent. The RF value is distance divided by the component divided by distance traveled by the solvent. Again, it is a ratio, so it has no units. Alright, last part, locating agent is a spray we use to convert colorless spots to color to make them colored so we are able to see them. Okay, and yeah, that is it for topic 6. regarding the equilibrium and rates of reactions, irreversible reactions, dynamic equilibrium, and separation methods for chemistry 0620 Cambridge IGCSE. Any questions in the comments below? And I'll see you in the next one.